In this video, I'm going to show how to integrate a third-party servo drive with an Omron NJ or NX series controller. Omron controllers are programmed with Teknic Studio, which provides PLCopen motion control instructions. Now, these are standardized motion control instructions that many different motion control vendors have included in their programming platforms. PLCopen motion control instructions use an axis object that links the application variables with the data exchanged between the controller and the servo drive. Now, Omron manufactures their own high-quality servo drives that automatically link with the axis object. This simplifies the integration process, but sometimes there is a need to use a third-party servo drive, and this requires a little more careful attention to the integration. The nice thing about Omron controllers is that they support the EtherCAT communication protocol, which is widely supported by many other servo drive manufacturers. However, just because a servo drive uses EtherCAT, it does not mean it will integrate well with Omron controllers. In addition to supporting EtherCAT, the drive and the controller must have a consistent application layer. Omron controllers use CANopen over EtherCAT. CANopen was a popular application layer originally implemented over CAN-based serial networks. CANopen is the most commonly used application layer for EtherCAT servo drives, but there are some servo drives that instead use Servo over EtherCAT. These would not integrate well with Omron controllers. Servo drives using the CANopen application layer have several objects called service data objects, or SDOs, and process data objects, or PDOs. These are defined by the device profile CIA402, which is the device profile for motion control drives. However, controller vendors and drive vendors do not support every function and every object that is defined in CIA402. So you need to check and make sure that there's sufficient overlap between the functions and objects that are supported by both the drive and the controller. The first item to check is to see what operating modes are supported by the controller and the drive. Omron controllers support 3 operating modes: cyclic synchronous position, cyclic synchronous velocity, and cyclic synchronous torque. If the drive does not support any of these, it cannot be integrated with the controller. Finally, we must confirm that all the required PDOs for the motion control application are supported by the drive. This involves having a good knowledge and understanding of how the high-level programming instructions interface with the PDOs exchanged between the controller and the drive. The best way to obtain this knowledge is to go through the integration process with a compatible drive. In this video, I'm going to walk through the integration steps for a Teknic ClearPath-EC servo motor. There are 5 main steps for building a motion control application using this controller and drive. Step 1 is the physical integration. This is the mechanical and electrical system design and installation. Step 2 is the configuration of the drive parameters. This is done using Teknic's ClearView 3.0 software. Step 3 is the configuration of the EtherCAT communication. This is done within Teknic Studio. Step 4 is the configuration of the axis object, also done within Teknic Studio. And step 5 is writing the application program using the PLCopen motion control instructions, also within Teknic Studio. This video primarily covers steps 2 through 4. For those of you looking for more resources on steps 1 and 5, I encourage you to check out our motion control workshop. Details of our workshop can be found by following the link in the video description. Step 1 is already complete. I have a simple setup to show some capabilities of an Omron-controlled ClearPath-EC motor. Here is the ClearPath-EC motor. It is not attached to any transmission or load other than this arrow clamped to the shaft to clearly show the shaft position. The black cable is the power cable. it plugs into a power distribution strip where power is provided by this 75-volt DC power supply from Teknic. You don't need to use Teknic's power supply, but this one is designed to handle high peak current demand and regenerated energy typical in motion control applications. The orange M12 cable contains conductors for the EtherCAT communication and for digital I/O signals. It connects to an M12 adapter that has ports for network patch cables for connecting to the EtherCAT network. I have a cable in port A connecting the ClearPath-EC slave to the Omron master. Additional EtherCAT slaves can be daisy-chained to port B on the adapter. For the I/O, I have two proximity sensors that I intend to operate as limit switches, where the drive will stop motion when the proximity sensor is triggered by the screw on the arrow tip. These signals are plugged into the I/O port on the adapter. I also have a USB cable connected to the drive. This connection is used to communicate with Teknic's ClearView software for drive commissioning and troubleshooting. It is not meant to be permanently attached. Now for step 2, configuring the drive parameters using Teknic's ClearView software. The software can be found on Teknic's website. So under Downloads, ClearPath-EC, Software, and here's the zip file to download and install. I've already done so. So I'll open the application and I'll plug in the USB cable. The drive should be recognized shortly. Good. The first thing I need to do is I need to switch from the access mode from monitor to full access. And this is going to allow me to write to the drive parameters. And when I write to them from ClearView, these values will be saved to the non-volatile memory on the drive. Now, I'm not going to overview all the drive parameters, but I am going to overview some ones that I consider to be most important. First up, we do have some I/O. And I want my proximity sensors to work as limit switches, where the drive will disable motion if they're triggered. So I have input A mapped to what I want to be my negative limit switch, and B, my positive limit switch. And the sensors that I used are normally open PNP sensors, so they're going to trigger when the input turns on. Okay? Now for setup, torque and speed settings. And for these, you want to consider the operational limits of your connected mechanical system. You also want to consider your application. I'm going to leave the maximum torque to be 100, but for the speed, I'm actually going to drop that down to, say, 2,000 RPM. There's also an option to have separate torque limits for different directions. This would be useful for a vertical application where you might want higher torque for lifting a load, but lower torque for lowering the load. Under additional features, there is a disable and stop option. And the default is to use dynamic braking. And this will disable the motor and use dynamic braking to very rapidly bring the motor to a stop. But if I had sensitive equipment on the load that was being moved, I might want to have a decelerate stop where I could specify a more gentle deceleration rate. And there are different stop settings depending on the input. So this is for just regular disabling of the motor. There's a separate setting for if the drive has a fault. You can either use the dynamic brake or just coast to a stop. Now for the tuning. Now, most servo drives have an auto-tune process. And that's just because manual tuning is a very tedious and time-consuming process. So in auto-tuning, the servo drive will excite the motor and automatically adjust the gains, usually to minimize settling time, while still having an acceptable level of audible noise. Teknic's auto-tune wizard is pretty nice in that it has a lot of safety checks to make sure that you're not going to damage your equipment. And there's more than just a checkbox to make sure that you've read the warning. You can also specify your peak torque limit here. You can kind of set how aggressive you want the tuning stimuli to be. You can specify a maximum velocity. Notice it's already grabbed our maximum velocity that we've already defined. And we can specify the mechanical limits. I'll select the move the mechanics by hand. And I'll just move this within the range somewhere between my proximity sensors. Now, the tuning process takes quite a bit of time, and it's pretty noisy. So I'm going to speed up the video here. All right. I'll disable the motor. And I'll treat this as being finished. Now for step 3, setting up the EtherCAT communication in SysMax Studio. Before opening SysMax Studio, the EtherCAT slave information file for the ClearPath motor must be included in the device library folder for SysMax Studio. This file can be found on the Teknic website, just under the ClearView installer file download. So this file needs to be placed in the following directory. So when you put it in there, SysMax Studio will be able to recognize the device. So with the ESI file in the proper location, I'll create a new project in SysMax Studio. And I'll select my controller, and I'll hit Create. The first item we need to configure is the communication cycle time. This is configured under Task Settings. So I'll double-click. So this will be the primary task, and I'm actually going to set the task period to be as small as possible, so 1 millisecond. Next, we need to add the ClearPath node to the EtherCAT network. I'm going to double-click on EtherCAT. Now, notice in the toolbox, we can go to Teknic Inc., and we can see that we have a ClearPath ESI file that's recognized here. And we could, offline, we can drag it and drop it on here and add it to the network that way. However, since we have a physical network already constructed, we can automatically merge this project to the actual network configuration after we assign unique slave node addresses. To do this, I'm going to go online with the controller, and then I will right-click on the controller image and go down to Write Slave Node Address. Yeah, so currently, the Teknic slave node is 0, which is reserved for the master. So I'm going to change this node address to be 1. And there's a little pop-up saying that you have to cycle the power of the slave to update the address. All right, so now I'll go ahead and do that. So I'll go offline, and I'll cycle the power. Right now, I'll go back online. I will right-click on the controller icon again and click Compare and Merge with Actual Network Configuration. And I'm going to apply the network configuration. Awesome. Now we have our Teknic node in the EtherCAT network. If we go offline, we can now click on our Teknic node, and we can adjust the settings. The first setting I'm going to adjust is enabling the distributed clock. This will provide the best timing accuracy. There are a few other parameters we need to adjust. Under Edit Setting Parameters, we have a set of parameters that will be written to the ClearPath drive in the pre-operational state. This would happen usually shortly after turning on the system. Now, we already configured most of these parameters using ClearView, and we do not want the controller to overwrite those values. So I recommend removing all but 3 parameters. This can be done by selecting each parameter and clicking Remove. So I'm going to go ahead and do that, but leave 3 of them. All right, I wanted to leave these interpolation time period parameters. Also, it's good to include polarity. Polarity would allow you to switch what direction is considered the positive direction. I'm going to leave the default as counterclockwise being the positive direction, but it's good to include that in case you need to switch that. And I'm going to open up the Teknic software manual to see what to designate these. So the interpolation time period parameters, they are related to the cycle time that we have defined already. So the Teknic documentation provides a table of what you should set these parameters based on the cycle time. And if you don't have, if your cycle time isn't in this table, there is an equation down here that you need to satisfy. But since I have a 1 millisecond cycle time, I need 1 for the period value and -3 for the index. All right, I will apply these and hit OK. Now we need to configure the objects to include in the PDO mapping. This will define the data that will be exchanged every task period between the controller and the drive. The inputs are data from the drive to the controller, and the outputs are from the controller to the drive. Now there are different options that are pre-configured. I recommend picking this first option here. It provides the most flexibility. But each setting could be edited by adding or removing different entries. Something to be aware of is that the ClearPath-EC drive only allows for up to 8 PDO entries. I'm going to add a couple more PDO entries here. I'm going to add the positive torque limit, and I'm going to add the negative torque limit. This will allow me to dynamically adjust these parameters. And hit OK. All right, now we have the EtherCAT communication established. Now for step 4, creating and configuring the access object. Click on the arrow next to Motion Control Setup and right-click on Access Settings and go to Add Motion Control Access. Double-click on MC Access 000. In the Access Basics settings, we're going to map the existing ClearPath-EC drive to be associated with this access. So this will be a used access, this will be a servo access, and we are going to select our ClearPath node. Now we need to expand the detailed settings. Now, if this were an Omron servo motor, these parameters would already be mapped to the correct PDOs. But here we need to do this manually. So there are some parameters here that have stars and exclamation marks. These ones are required. Otherwise, we can't do any application. So we're just going to go through the process of selecting the appropriate parameters. And you don't have to map all of them, but I like to map as many as possible. All right, now for the digital inputs, it's a little trickier, but these are mapped to our digital inputs. And this can be found in the software reference manual. Here we go. This is the digital input objects. All right, that looks good. Now we just work our way through the other parameters. I'm going to go through these pretty quickly here. I have an app note on our website that provides more detail on these settings. And you can just follow the link in the video description. So here we have the unit conversion settings by clicking the ruler icon here. And the first thing up here is we pick what our operational units are going to be. Since I have a rotary application, I'll pick degrees. And this command pulse count per motor rotation, this relates specifically to your drive, usually related to your encoder resolution. I have an enhanced resolution position model that provides 51,200 counts per revolution. For our work travel per revolution, we're going to put 360 degrees per revolution. It would be different if we had a transmission attached. All right, next we're going to update our operation settings. And we do need to specify an appropriate maximum velocity. I'll use the peak velocity of this motor, which is, it'll end up being 23,700 degrees per second. And our maximum jog velocity, I'll set to be something smaller, 120. I'm going to leave acceleration to be 0, and that's going to mean that there's no limit applied to the acceleration. In other operation settings, I'm going to only change the maximum positive torque limit to be 100 and also for the negative torque limit to be 100. The default was set to be 300 because Omron servo drives, their percentage is relative to the rated torque, whereas Teknic servo drives are relative to the peak torque. Now, these limits, these maximum positive torque limit and maximum negative torque limit, these values will only take effect if we added the positive and negative torque limits in our PDOs. If we wanted to, we could apply some software limits. I'm just going to rely on my hardware limit switches for that safety function. Software limit switches, they only take into effect after a homing routine. And that brings us to the homing. Now, the Teknic servo motors, they do have different homing methods that can be done by the drive itself. For Omron controllers, they handle the drive, or they handle the homing internal to the controller. Different homing methods are available. I'm going to use limit inputs only, and I'm going to use the start homing in the negative direction. And so we'll travel until we hit the negative limit switch, and then we will turn around, and then once our limit switch turns off, that will define the home position. And we can also define the velocities for these different moves. We also have an option of putting in a home offset or home compensation. What I'm going to do is I'm going to add a homing compensation of 175 degrees. After the home input is triggered, it'll move 175 degrees and then apply that position as being the home position. So it'll be the arrow will be roughly horizontal. And I'll use 200 degrees per second for the velocity of that move. All right, next up is the count mode. This has to do with how the controller keeps track of position. Now, for most applications, you'll just want to use linear mode, but in applications where there's an undefined amount of travel, you're going to have to use the rotary mode. So in applications such as an indexing table or a conveyor belt, you'll want to use the rotary mode. I'm going to leave mine at the linear mode. The Teknic motors do use an incremental encoder, so I'll leave that there. There's also a selection for how the drive treats position, and I'm going to leave these at the default. It has to do with really using 32-bit signed integers for the PDO exchange for the command and actual position between the controller and the drive. And these settings have to do with how the PLCopen motion control power instruction interfaces with the power drive system's state machine. And I'm going to leave these at the default. All right, this concludes the access configuration. The PLCopen motion control instructions can now be used to control the ClearPath servo motor just as they would an Omron servo motor. Programming the application is outside the scope of this video, but I have a previous application that I built for my motion control workshop, and I just modified it for this specific setup I have here. So besides adding some programs with the motion control instructions, I also added an HMI, a human-machine interface. For those of you interested in HMI integration and programming, we offer a workshop on that topic as well. This area contains the operational status of the axis as well as controls for enabling, disabling, and resetting the axis. This area contains the application controls, so we can select what application we're going to use, and these buttons are for triggering or enabling actual motion. This area defines the motion parameters that are used in the application, And this area shows the real-time values of actual position, velocity, and torque, and plots them on trend lines. The controller receives the value from the drive every millisecond, but the values are only displayed every 100 milliseconds. So it's actually the average of these 100 values that are plotted as the thick line, and then the maximum and minimum of these 100 values are plotted as thin lines. And I can select what we're going to plot. So I'm going to switch to absolute value of the velocity. And I'll just move this by hand. And I'm trying very carefully to move this at a constant velocity, but it's very difficult for me to do so. It's not so difficult for the jogging controls. I just hit my positive limit switch, and that caused this error in the axis. So to enable it, I need to press reset, and then I can produce motion in the opposite direction. There's a button here that allows me to adjust the positive and negative torque limits. So I might drop down the positive torque limit to be considerably lower. And let's show the absolute value of the torque. So still quite a bit higher when I push on it in the positive direction, and the torque resists me in the negative direction. For the other direction, it actually maxes out at only 3% of the torque. I'll use a spring so we can see this. All right, we just produced an error, and this is a following error, not from our settings on the axis, but settings on the drive itself. So in ClearView, if we go to full axis mode, we have a pop-up that says that the EtherCAT master has to have the drive being disabled before we can make any changes. So let's go ahead and do that. And that's just to prevent conflict in control. All right, now we can adjust the following error limit settings. And I'm actually going to select this to not enforce shutdowns. And then similarly, we need to switch back into the monitor mode before we can enable the drive using EtherCAT. So now, we don't have a shutdown with excessive following error. I'm going to bring our positive limit torque, our positive torque limit to be back up to 100%. There's also a setting here for the stroke time, and this setting has to do with the next two applications, triangle move and smooth move. So we can set that to be a move to take 3 seconds. I'll select triangle move. Oh, now notice it switched to home. That's because for these moves, the drive has to be homed first. So let's go ahead and take care of that. And this just performs the homing routine that we already defined in the axis object. Yeah, so now in our position plot, we are at 0 position. And we can do our positive, we have a couple different moves. One, to add 90 degrees. And the other, I'm sorry, to go to negative 90 degrees. So these are absolute positions relative to 0. So it's called a triangle move because in the velocity profile, it looks like a triangle. For the smooth move, instead of having constant acceleration, it has constant jerk. So it smoothly transitions, it ramps up the acceleration. And these parameters are, again, selected to fit in that, to complete its move in the desired time. So this is actually not an input in the motion control function block, but rather I'm using this value and calculating what the velocity, acceleration, and jerk limits need to be in order to complete the move in the desired time. And this is a topic that is covered in our motion control workshop. Let's select a much more impressive move. So that completes the move in 0.05 seconds. So it requires much higher velocity to do so. And here's an application that shows just some other features for PLCopen motion control instructions. So this shows off the blending, where you can produce a blended move where you can transition from one velocity to another velocity without stopping. And it also shows cycling and sequencing. More advanced features would involve coordinated motion of multiple axes that can't really be shown with this setup here. So this concludes the demonstration of controlling a Teknic ClearPath-EC servo motor with an Omron NX series controller.